So gases are one of our three states of matter. We talked about way back in chapter 1 when we saw that cats can be both solid and liquid. They cannot be gases, unfortunately. The physical properties of gases can be manipulated and measured much more easily than those of solids or liquids. So that's because gases have a low density, they're compressible, and they're fluid. So they're easy to manipulate. So compressible just means that you can squish it, essentially. If you had a syringe full of a solid, like a cotton ball, and you had a syringe, well, a cotton ball is not a good example, I guess. Like some rocks. You have rocks in your syringe, or you have water in your syringe. When you push down on your plunger, you're going to release either of those things, or you're going to get a lot of pushback and you won't be able to release. So you won't be able to push down on the plunger. But you have a gas, even if you can't release the gas, if it's attached to a closed system, you can push down on the plunger and you can compress that gas without a ton of pushback from the gas. So that's what it means to be compressible. So, because the physical properties of gases can be manipulated and measured easily, the mathematical relationships between the properties of gases are some of chemistry's earliest formulas. So you will see some formulas that date very far back, and those are based on gases and their mathematical relationships of their properties. So what are those properties that we want to talk about? There's 5 main properties that we're going to talk about with gases. Mass isn't really one that is too important because we can get to mass from moles, or we can get to moles from mass based on our molar mass. So the 4 that are really important are the amount in moles, the volume, usually in liters or milliliters, the pressure in atmospheres or kilopascals or bars or psi. So those are all different units of pressure, and temperature, which for most of our equations is going to have to be in Kelvin, not degrees Celsius or Fahrenheit, though it might be given in degrees Celsius or Fahrenheit in the problem and you have to convert it. So these are our main 4 properties that we're going to talk about. All right, so what is pressure? Pressure is equal to force over area. You should have seen this back in experiment 5 in the lab. So gases exert pressure on surfaces, and that pressure is measured as a force exerted on a given area of a surface. So P equals F over A. The confined gas exerts pressure on the interior walls of the container. So if you have a balloon, the air inside of the balloon is exerting pressure on the interior walls of the balloon. But we also have gases in our atmosphere that are exerting pressure on everything they come in contact with. So there are gases exerting their pressure on you right now. Gas pressure is often measured using a barometer. The first barometers consisted of a tube sealed at one end, inverted in a pool of mercury. So you can imagine why we don't use those anymore. The gases in the atmosphere push down on the mercury in the pool and force mercury up that tube. The height of the mercury column gives us atmospheric pressure in millimeters of mercury, which is one of our units of pressure. That was one of the earliest units of pressure. So a little picture of what that early barometer looks like is up here. So you have your pool of mercury, you have atmospheric pressure, gases in the atmosphere pushing down on that mercury, which is causing some of that mercury to rise up this column that has a vacuum on the end because it's sealed. So the mercury will never rise all the way to the top because there is some gas that is present up in the end of the tube. So we measure the height of the mercury from where it starts, where the tube starts in the pool, to where the mercury ends. That height of mercury tells us about the pressure. Another unit of pressure is called the torr, and that was named for the inventor of the barometer, and his name is Torricelli, in case you were interested. So, torr are actually equivalent to millimeters of mercury. So those are equivalent units. In the laboratory, we usually measure it with something called a manometer instead. In this case, mercury is added to a U-shaped tube. So look down here at this picture. The mercury is in here, in the U-shaped part of the tube. One end of the tube is open to the atmosphere, which is this end. The other end is attached to a sealed container with a gas that you want to measure the pressure of. If the pressure of that gas sample is equal to atmospheric pressure, then you're going to have the same amount of pressure coming from the gas sample as coming from the atmosphere, which is going to make that level of mercury equal on both sides of the tube. If the gas pressure is not equal, which it isn't in the example that they gave you, so you can see that there is more pressure from the gas sample. It's pushing the mercury down further than the atmospheric pressure is pushing the mercury. So the gas sample has higher pressure than the atmosphere. And gas pressure comes in many units. Seen. The SI unit for pressure is the Pascal, which is equal to a force in newtons exerted on 1 square meter. So newtons is the SI unit for force. So a Pascal, if you need to convert units, a Pascal is equal to Newton over square meters. The English unit, pounds per square inch, or PSI, that one you've probably heard of before because you've probably filled up the air in your tires in your car before, and that is measured in PSI. That's a measure of how many pounds of force a gas is exerting on 1 square inch of a surface. And atmospheric pressure at sea level is approximately 14.7 psi. Pressure units are based on pressure measurements at sea level, and the average mercury column height, so we're going back to that old barometer where we measured the height of mercury, that average mercury column height is 760 millimeters of mercury. This measurement defines the standard atmosphere. So atmosphere in this case is not the air surrounding the Earth, the layer of air surrounding the Earth. In this case, atmosphere is a unit of pressure. So 1 atmosphere is equal to 760 millimeters of mercury. And 1 atmosphere is the pressure at sea level. Some other units you might see in the lab or in the textbooks are atmospheres, kilopascals, which is just a metric multiplier of pascals, bars, and millimeters of mercury. And the conversions between those are all here. So 1 atmosphere is equal to 1.013 bars. So if you remember, in our last section, we talked about the standard conditions for enthalpy, and one of those was that the pressure of your sample was 1 bar. But now we're learning that 1 atmosphere is a little less than 1 bar because 1 bar is a little bit bigger. So you have 1.013 bars in 1 atmosphere. And then we have kilopascals, millimeters of mercury, torr, which is the same as millimeters of mercury, like I said, and psi. So let's convert a gas sample pressure of 1.69 atmospheres into millimeters of mercury. So we have 1.69 atmospheres. And if we look at our conversion, 1 atmosphere is equal to 760 millimeters of mercury. So that gives us a conversion factor. So 1 atmosphere and 760 millimeters of mercury. So now we can cancel out atmospheres and we'll end up with the unit that we're looking for. So we've got 1.69 times 760. So 1.69 atmospheres is equal to 1284.4 millimeters of mercury. And that's all it takes to convert between pressure units.